A parameterized smooth plane curve is a smooth map gamma from alpha beta onto R2. A curve is called regular if the first derivative is not equal to 0 for all t in the interval alpha beta. If the absolute value of the first derivative of the function is equal to 1 for all t in R, the curve is called unit speed. The tangent is defined as the first derivative of the function. The normal is defined as a 90-degree rotation of the tangent. The pair t and n is called the Frenet frame of a plane unit speed curve. For a unit speed curve, curvature is defined by the absolute value of the second derivative of the function. The sine curvature of a plane curve is defined by the inner product of t' with n.
A parameterized smooth space curve is a smooth map gamma from the interval alpha beta to R3. For a space curve, the normal is given by the normalization of the second derivative of our curve. The binormal is the cross product of the tangent with the normal, and the torsion is given by the negative of the inner product of the derivative of our binormal with our normal. The torsion of a space curve is the rate of change of a curve's oscillating plane, which is the plane spanned by the set Tn.
The surface patch is a set S in R3 such that there exists a homeomorphism where X is mapped from U to S, where U is an open set. That is, X is bijective and both X and X inverse are continuous. A Gauss map is a unit normal vector field on a surface S, a smooth map N mapped from S to R3. N to the X equals the cross product of XU and XV over the modulus of this cross product. Defines a Gauss map N on the surface patch S equals X of U. by setting n equals to n to the x composed with the inverse of x. The coefficients of the first fundamental form are e equals the inner product of xu and xu, f equals the inner product of xu and xv, and g equals the inner product of xv and xv. The coefficients of the second fundamental form are e equals the inner product of n to the x and xuu, f equals the inner product of n to the x and xuv, and g equals the inner product of n to the x and xvv. The Gaussian curvature is defined as k equals eg minus f squared all over eg minus f squared. The mean curvature is defined as h equals eg minus 2ff plus eg all over eg minus f squared. The normal curvature is defined as kn equals the inner product of n composed with gamma and gamma double prime. The geodesic curvature is defined as kg equals the inner product of the cross product of gamma prime with n composed with gamma and gamma double prime.
The mean curvature of a surface you encountered was equal to 0, making it a minimal surface. A surface X in R3 is minimal if and only if its mean curvature vanishes identically. A direct implication of this definition is that every point on the surface is a saddle point with equal and opposite principal curvatures, which are the eigenvalues of a shape operator at the point, measuring how the surface bends by different amounts in different directions at that point. The first non-trivial examples, the catenoid and helicoid, were found by Meunier in 1776. Euler proved that a minimal surface is planar if and only if its Gaussian curvature is 0 at every point, so that it is locally saddle-shaped. The existence of a solution to the general case was independently proven by Douglas and Rado. Although their analysis could not exclude the possibility of singularities, Osterman and Gulliver showed that a minimizing solution cannot have singularities. However, There's still much more to learn about the world of Curvémon.
Good luck on your quest for knowledge.